Hi class, welcome to our third lesson on Chapter 9. We're on rotations today. What a rotation is it's another transformation. This time it's a transformation that turns every point a specified angle and direction about a point. A specified angle, so that's like how many degrees it turns or rotates, and a direction, we would say that the direction is it turns counterclockwise or clockwise about a certain point. So we have what's called the center of rotation. The center of rotation is the point everything is rotated about. So as you can see in this picture, triangle ABC is rotated to triangle A prime, B prime, C prime, and it's rotated about the point P right here. Okay, so that's our center of rotation. As you can see, rotation is another form of isometry. The triangle stays the same shape and the same size. It doesn't enlarge or doesn't shrink. So it's a congruent transformation, and it turns about a point, and that point is the center of rotation. We also have what's called the angle of rotation. The angle of rotation is the measure of the angle that determines how far to rotate the image. So again, triangle ABC is rotated 60 degrees in this direction, so we would call this a clockwise rotation. And as you can see, this angle from C to C prime is 60 degrees. 60 degrees clockwise. So that's what we call the angle of rotation. And every point is rotated 60 degrees. If you were to do this, if we were to take a protractor and measure angle A, or point A to A prime, this angle would also be 60 degrees. Every point from triangle ABC to triangle A prime, B prime, C prime is rotated that 60 degrees clockwise angle. That's called the angle of rotation. So I have another example up here just to reiterate it. I have quadrilateral ABCD. This time it is rotated counterclockwise to quadrilateral A prime, B prime, C prime, D prime. It's rotated about point R, so we would call R the center of rotation, and the angle of rotation would be something like 40 degrees counterclockwise or something like that. Whatever the angle is from D to D prime, this angle right here. Or point P to point P prime. Again, that angle is going to be congruent because they're all rotated the same number of degrees. We'll do this one in class together. So we're going to get on to rotational symmetry. Here's what rotational symmetry is. A figure has rotational symmetry if it can be rotated less than 360 degrees and land on top of itself. So if we could rotate a figure such as this regular hexagon right here, we can rotate this and it would land on top of itself. So just watch as I do this here. So right now I could rotate it right here, and it lands on top of itself. And I could rotate it right here, and it would land on top of itself. So this has rotational symmetry. It can be rotated less than a full circle. 360 degrees is a circle. It can be rotated less than that and have the figure land on top of itself. The order is the number of rotations less than 360 that place the image back on top of itself. So it's basically the number of times I can rotate a figure and have it land back on top of itself. So let's take this regular hexagon again. And how many times can I rotate this where it lands back on top of itself? So we have 1, 2, 3, 4, 5, and then 6 puts it right back to where it was, right? And so this one, the order is 6. And any regular polygon will have the same order as it has sides. So an octagon, it can be rotated 8 sides. A regular nonagon can be rotated 9 sides. Whatever a regular polygon has for sides, it has the same order. It can be placed on itself that many times. So now we have lastly the magnitude. And the magnitude is the measure of the smallest angle which will rotate the figure on top of itself. So what is the angle measure from here to there? Right? Here is where it starts, And the smallest angle that will rotate it back on top of itself is right here. So if we take a look at this for a second, here is like the center of rotation. And so this segment, this red segment right here, has to be rotated so that it gets on top of this green segment. And it can be rotated again where it gets on top of this purplish segment, pinkish purplish. And then this bluish purplish segment, and then the brown segment, and then the blue segment. How many degrees is each one of these angles? Well, there's 360 degrees in a circle, and there is 1, 2, 3, 4, 5, 6 angles. So the magnitude is 360 divided by the order. The order is 6, so 360 divided by 6. This can be rotated, the smallest it can be rotated is 60 degrees, and then it lands back on top of itself. So that's the magnitude. It's the measure of the smallest angle, which will rotate the figure onto itself. In the hexagon, in any regular polygon, it's 360 divided by the number of sides, which is the order. Let's practice this again. Here we have the star. Does it appear to have rotational symmetry? Well, if I, again, rotate it, right there, it would fit on top of itself, right? So there is 1 time, right? And then I could rotate it again, so it would be 2 times, 3 times, 4 times, and then back up at the top again would be 5 times. So does the star appear to have rotational symmetry? Yes, it does. I could rotate on top of itself 5 times. So what is the order? The order, it can be rotated 5 times before it is placed back on top of itself again for that full 360. So the order is 5. The magnitude is always 360 divided by the order. And the order is 5. So what is the degree angle from here to there? 360 divided by 5 is 72 degrees. So the magnitude, 72 degrees. 360 divided by 5. We'll try one more of these, a regular dodecagon. Again, a regular polygon, its order is as many sides as the figure is. If a dodecagon has 12 sides, then the order is 12. What would be the magnitude? The magnitude is 360 divided by the order. And if it can be rotated 12 times, 360 divided by 12, the magnitude is 30 degrees. All right, we finish off with this one. The translation xy yielding x plus 2, y plus 5 is applied to the triangle below, followed by a 90-degree rotation counterclockwise about the origin. What is the image of 2, 3 after the translation and the rotation? So we have 2 different transformations going on here. The first one is a translation. So the whole triangle is moving right 2 units and up 5 units. So I could do this to the entire triangle, but being that the only point I care about is 2, 3, we'll just do it to this point right here, which is right 2 up 3. So the first thing I'm going to do is I'm going to translate it, x plus 2, y plus 5. So 2, 3, I'm going to go 2 units to the right and 5 units up. So there is, like if I were to call this point right here A is at 2, 3. This one up here would be A prime. I have moved it 2 units to the right and 5 units up. So if A is at 2, 3, A prime would be at my x coordinate, I would add 2, so 2 plus 2 is 4. And my y coordinate, I would add 5, so 3 plus 5 is 8. So A prime right here is at 4, 8. Now I'm going to rotate this 90 degrees counterclockwise. So a 90 degrees counterclockwise rotation would rotate it somewhere over here, right? That's counterclockwise. And 90 degrees somewhere over into the second quadrant. So I have gave you these helpful hints. We could again do this with a protractor and a compass, which we'll do tomorrow. But for now, I'll just give you the hint. If we want to rotate it 90 degrees clockwise, this is what we do. If we want to rotate it 90 degrees counterclockwise, this is what we do. So for every point xy, which our point is 4, 8, if I want to rotate it counterclockwise 90 degrees, my y goes to the front, and I change the sign on y. So it was 8, now it's a negative 8. My x coordinate goes to the back, so it acts as the y coordinate. So my 4 is now my y coordinate. So a 90 degrees counterclockwise rotation will be left 8, 1, 2, 3, 4, 5, 6, 7, 8, and up 4, 1, 2, 3, 4. Right here is now where A double prime is. And let's write that down here as well. A double prime is at negative 8, 4. So now this is my answer, and if you kind of like think logically about this here for a second, the origin is the center of rotation. So this is what point A prime is rotated about. If I were to connect segment from the origin to A prime and the segment from the origin to A double prime, this angle right there is 90 degrees. It's a 90 degrees counterclockwise rotation. We'll do more work on rotations when you get to class tomorrow.